Welcome back to the fifth day session of National Enrichment Program in Mathematics 2021, conducted by the Department of Mathematics of Sacred Heart College, Chalakudi. I hope all the participants had a wonderful time listening to various topics of mathematics. So, today we have the fifth session. So, may I invite Nima, Faculty of Mathematics Department, SH College, Chalakudi, to introduce the speaker.
Am I audible?
Yeah.
Yes.
Okay. Good evening, everyone. I am here to introduce you to the research person of the day, Ms. Ramya Nair. She did her bachelor's from Ramya Nair College, Mumbai, and master's from Mumbai University. She is currently a senior research fellow at IISER Pune. With such an experience, I'm sure she will inspire us with her talk. I would like to welcome Ms. Ramya Nair to NEPM 2021 on the behalf of Department of Mathematics, Sacred Heart College, Chalakudi. Welcome, ma'am.
Thank you.
So over to Ramya Nair.
Okay. So, good evening, everyone. Thank you for giving me this opportunity to talk to you guys. So I'll start sharing now. So is it visible?
Yes.
Okay. So the aim of my talk would be to give you an instance of how seemingly unrelated areas of mathematics come together to solve beautiful problems. So in my talk, I've not tried to be very rigorous. I just want to give you a glimpse of how these ideas work. So if you have any questions at any point of time, please feel free to stop me and ask them. Okay, so this talk would also provide, I hope that it provides an introduction into the subject of Galva theory, which some of you might not be familiar with. So I have tried to include as many examples as possible so that I can navigate through the theory. So don't worry, even if you don't understand some technical definition or what a theorem really means, you can just think about those in terms of easy examples. Okay, so So Galva was a French mathematician who made seminal contributions to the subject before even reaching the age of 21. He unfortunately died when he was 21 years old, but the work that he did before that actually was instrumental in the development of group theory and a subject called Galva theory. Is my are my slides moving?
Yes.
Okay. Okay. So yeah. So in mathematics, Galva theory was originally introduced by Evariste Galva, and it provides a connection between field theory and group theory. So what Galva was doing at that particular time was he was studying the roots of polynomials. So the birth of the subject called Galva theory was caused by the following question. The question was, does there exist a formula for finding the roots of a fifth degree or higher polynomial? So we all know that for a quadratic, there is a formula for finding out the root of polynomials. So the question was, is there such a formula for any polynomial of any degree? So this question is what motivated Galva to study the roots of polynomials and then eventually lay the foundations of group theory and Galva theory. Okay. So my slide to me doesn't seem to be moving. Can I just stop sharing and do this thing once more? The sharing part?
Yes, sure.
Okay. Ah, so yeah, as I was saying, Galva was studying the roots of polynomials, and he was interested in solving that question. That is there a general formula to find out the roots of uh, any polynomial? So the title of my talk was Insolvability of a General Quintic. So a quintic polynomial is a degree 5 polynomial with coefficients in some field like rationals or real numbers or complex numbers. The result that I intend to discuss here can be vaguely put as follows, that there is no general formula to solve a polynomial of degree 5 or higher. Okay. So the reason why this is true is because of a result from group theory, which says that the group Sn is not solvable for n greater than or equal to 5. So do you guys know what the group Sn is? You might not. Yeah, the symmetric group on n symbols. So you might not know what solvability is. That I'll discuss later. But the reason for the answer to that question being no is a fact from group theory. So to see all this, we have to connect polynomials, their roots, to fields and groups. So we'll first talk about field extensions, and then we'll talk about something called the Galva group, and then how all these can be used to prove whatever we intend to prove. Okay, so so the first topic that I'll be discussing is fields and field extensions. So a field, as most of you might know, is a commutative ring with identity in which every non-zero element has an inverse. So examples of fields are rational numbers, real numbers, complex numbers, etc. So now what is a field extension? Suppose you have a field F, then when is a field L said to be an extension of F? So a field L is said to be an extension of F if there exists an injective homomorphism from F to L. So we denote it by this symbol. It is said as L over F. So here, what this means is L is a bigger field which contains F as a subfield. So yeah, so if any field L is an extension of F, it can be viewed as a vector space over the smaller field. So that notation denotes the dimension of L over F as a vector space, and we call it the degree of extension of L over F. So as an example, you can see that the field of complex numbers, it can be viewed as a vector space over R with bases 1, I. This is because you know what complex numbers look like, right? They are A plus IB, where A and B are both real numbers, and I is the square root of -1. So you can think of complex numbers as a two-dimensional vector space over R with bases 1 and I. Okay. So what is it that we intend to do? So suppose we have a polynomial x squared minus 2. So this is a polynomial over the set of rational numbers. You know what the roots of this polynomial are, right? So the roots of this polynomial are square root of 2 and minus square root of 2. So we know that the roots of this polynomial is completely contained in R because square root of 2 is an element of R, and so is minus square root of 2. And we also know that the square root of 2 is not a rational, it's not a rational number. So our aim is to find out the smallest field that contains the roots of this polynomial x squared minus 2. So we are about to construct a field like that, which is in between Q and R, such that it contains a root, so that it contains all the roots of this polynomial x squared minus 2. So for that, we define a set Q of root 2, where the elements look like a plus b into square root of 2, where a and b are rational numbers. So at a first glance, we can see that this set that I have defined is not a field, because elements like square root of 2 do not have inverses. So what I do is I add in the minimum number of elements that I need so that this becomes a field. This set is converted into a field. So I just add all the required elements. I add all the elements that are there in that set. I subtract them. The basic arithmetic operations, I just add all those elements. And whatever resultant field I get, that is called Q adjoint root 2. So now Q adjoint root 2 is a field because I constructed it that way. So this is a field which contains the set of rational numbers, but it is not equal to R either. It is between, it is a proper, a subfield of R, because, you know, elements like square root of 3 or any of those other irrational numbers like pi or e are not there, because you have constructed this out of that set which involves only these 4 basic operations. So there is no way you can get to elements like pi or square root of 3 in that field. So this is an example of a field extension. So this field Q adjoint root 2 is an extension of the field Q, which contains all the roots of this polynomial x squared minus 2. So throughout the talk, we'd be interested in fields that contain roots of polynomials. So that is going to be our main aim, to see how we can find subfields of complex numbers or real numbers that contain the roots of certain polynomials. So extension by radicals. So what do you mean by that? So you have a field extension L over F that is said to be a radical extension if you have a finite number of fields Li such that the smallest field, I mean, you just have a sequence of field extensions. So that the final field is L and your base field, I mean, the smallest one is F, with the property that each Li plus 1 is is constructed by adding one element alpha I, is not by adding, by adjoining one element alpha I, with the property that alpha I to the power ni belongs to the field Li. So we'll see an example and you'll understand what I mean by this definition. So yeah, so a radical extension is obtained by adding the nth root of an element in the preceding field. So that is the gist of that definition that I wrote. So here's an example. You have Q root 2, the field that we constructed earlier, and Q is a subfield of that, with the property that square root of 2, the whole square, is an element of rational numbers. So we are essentially looking at such extensions where, it is the bigger field, the extended field is created by adjoining elements that are whose nth power belongs to the previous field. So in this case, square root of 2, we add square root of 2 to Q. And this is a radical extension because the square of that number is a rational number. So similarly, you can adjoin the square root of another number, for instance, say 3. So Q contained in Q root square root of 3 is also a radical extension. And so is this field extension where you have Q adjoined I. So square root of -1 is the complex number I. So we can construct fields. We can construct a field Q of I, which is, you are adjoining I to Q. So we had, okay, so the polynomial x square plus 1, that has no real roots, right? Both the roots are imaginary, plus I and minus I are the roots of that polynomial. So it's clearly, I mean, the polynomial has no real roots. So Qi is the smallest field containing all the roots of that polynomial, x squared plus 1. So a polynomial that has all its roots in a radical extension of Q are said to be solvable by radicals. Just a second, my screen is stuck. Okay. So in the previous slide, I was talking about what are polynomials solvable by radicals. So yeah. So the quadratic equation ax squared plus bx plus c, this we all know since our high school maybe, that the roots of this polynomial are given, it's given by a formula, right? It's minus b plus minus square root of b square minus 4ac by 2a. That is the general form. That is the general formula for finding out the roots of a quadratic. So then, what would be the field that contains all the roots of this polynomial? So here, in your formula, x equal to minus b plus minus square root of b square minus 4ac, your minus b and your by 2a are all rational numbers, so they are already in Q. So the only thing that might not be there in Q is that square root, right? B square minus 4ac. So if you just adjoin that to Q, then this field Q adjoined with square root of b square minus 4ac would contain all the roots of ax square plus bx plus c, where a is a non-zero real number, or I mean a rational number in this case. So hence we say that a quadratic polynomial is solvable by radicals. So let's look at another polynomial. So the polynomial is x cubed minus 2. So here I am claiming that the extension that I have written, q contained in q adjoined with cube root of 2 contained in cube root of 2 comma square root of minus 3, where that last field is nothing but square root of minus 3 adjoined to the previous field. So I'm claiming that all the roots of x cubed minus 2 is contained in that last field. So you can think about how that is. So a hint would be to look at the roots of this polynomial. I am guessing you all know how to find out the roots of this cubic polynomial. So if you look at the roots of this polynomial, you would understand why all the roots of this polynomial is contained in that field. So, okay, this is something called a tower law. So if you have F contained in E contained in L, they're all fields, then you have this kind of a formula. So that notation was for the dimension of L as a vector space over F. So that dimension is equal to the product of dimensions of the in-between fields. So we can look at an example. So the example is you have this tower of fields, say Q is contained in Q adjoined with square root of 2 contained in Q adjoined square root of 2 comma square root of 3. So we can look at what are the individual dimensions, and then what is the product, and what is the dimension of L over F. So the dimension of Q root 2 over Q would be 2, because the basis of Q root 2 over 2 would be 1 and root 2. So the dimension is 2. Similarly, when you have Q root 2 root 3 over root 2, you just have a basis consisting of 2 elements, which is 1 and square root of 3. So what does the tower law say? The tower law says that the dimension of L over F is equal to the product of dimensions of L over E and E over F. So the basis for the bigger field, if we compute it without using the tower law, it will have to be 1, square root of 2, square root of 3, and square root of 6. So if anyone is not following what is happening, please stop and ask me.
Ma'am, q root 2 comma root 3 is not understand.
Okay, so what is q root 2 comma q root 3 is your question, is it?
Yes, ma'am.
Yeah. So you understood what q root 2 is, right? Uh, so you understood what q root 2 is, right?
Yes, ma'am.
Yeah. So q root 2 is a field. I mean, we constructed it as a field. So we use the same kind of construction for adjoining square root of 3. So there the set would look like a plus b into square root of 3, where a and b are elements of q root 2.
Okay, ma'am.
Okay. So that is the field q root 2 q comma root 3. So then the basis for that would be 1 square root 2 square root 3 and square root of 6, because you will end up multiplying square root of 2 and square root of 3 in that field. So you need a square root of 6 as well. So this is an instance of the Tower law where you can compute the basis for each of them and see that the law holds. Okay. So now we have this concept of Galva group. So what is a Galva group? So you have an extension L over F. So the Galva group of L over F is defined by the set of all automorphisms of L which fix F. All right. So you can verify that this set forms a group, and this group is called the Galva group of L over F. So once again, I'll tell what the group is. So this is the set of all automorphisms of the field L that fix the field F. So a trivial example would be Galva group of Q over Q. So can anyone tell me why is it identity?
Q to Q is an automorphism.
Yeah, so the condition is that it should fix Q. So there is no other choice, right? It should be an automorphism of the bigger field such that it fixes the smaller field. That is restricted to the smaller field, it should be identity. But here both the fields are the same. So it cannot have any other choice. So that is just identity. So, okay, so the next question is, what would the Galva group of Q root 2 over Q be? So it might help to think of this as a vector space isomorphism, as well, because these are vector spaces over the smaller field. So for it to be a field isomorphism, it has to be a vector space isomorphism and something more. So all you have to see in this case is where can you send 1 and root 2, correct? So 1 cannot go to anything else because you want to fix Q. So 1 has to go to 1. So now what choices do you have for square root of 2? That is all you have to see. So we'll see it later what can happen to this. So so this is the hint. Since Q has to be fixed, you take any automorphism and you look at the image of this element. A and B are both rational numbers, so they have to be fixed. So you just have to worry about where can you send square root of 2. Okay. So now this would give you an answer to that question as to where can you send this element square root of 2 in the previous example. So suppose you have a polynomial. So here your F, the smaller field in our case is always Q, and the bigger field is some extension of Q. So if you have a polynomial in Qx and you have an extension L over F, and you have a root of that polynomial which is in the extension L, and you have an element of the Galva group, then what does that automorphism, what does that element of Galva group do to the polynomial P, and what does it do to the what does it do to P of alpha? So since alpha is the root of this polynomial, P of alpha is going to be 0. So what happens to sigma of P of alpha? So you know that the coefficients of this polynomial are rational numbers, and this automorphism belongs to the Galva group of L over F, which fixes Q. So it fixes all the coefficients. So then sigma of P of alpha becomes P of sigma alpha. So since P of alpha is 0, sigma of P of alpha is also 0. So what you end up getting is you have a polynomial, you take an element of your Galva group and make it act on the polynomial. Then the root of that polynomial is mapped to another root of that polynomial by an element of the Galva group. So it says that if alpha is a root of Px, then so is sigma alpha for every element in the Galva group. Is that part clear? This is important. Is this okay?
Repeat, please.
Okay. So what I'm saying is, if you have a polynomial P of x in Q of x, and you have an extension L over F. So, and alpha is a root which belongs to that extension. So you can think of those polynomials that we discussed before. So x square minus 2, say. So you know that, okay, so you take this, an element of the Galva group, you know that it fixes Q. So the polynomial, what happens to that polynomial? So if you suppose, so square root of 2 is a root of x square minus 2. So square root of 2, the whole square minus 2, you act the element sigma on it. So then what does it do?
0.
Yeah, exactly. So the point is, if you have alpha as a root, then sigma of alpha is also a root of the polynomial. Is that okay?
Okay, ma'am.
Yeah. So this is what it does. Like the Galva group permutes the roots of polynomials. So if you have a polynomial and if you have a root in an extension, then any element of the Galva group of that extension over F would just permute the roots of that polynomial. So that is the endpoint. That is, if alpha is a root, then so is sigma of alpha. Okay. So now you have an extension L over F, and a polynomial is said to split in the bigger field if you can write that down as a product of linear factors. So L over F is said to be the splitting field of a polynomial if the polynomial splits in L of x. So for instance, x squared minus 2 does not split in Qx because the roots of that polynomial are not there in Q. So you cannot write it as x minus square root of 2 multiplied by x plus square root of 2 in Qx, because in Qx the coefficients have to be in Q. So this polynomial splits in Q adjoint square root of 2. So such a field where this polynomial splits into linear factors, and the minimal such field is called a splitting field of that polynomial. So the difference is x squared minus 2 splits completely over R also, because square root of 2 and minus square root of 2 are both real numbers. So it splits completely over R as well, but that is not the smallest field where it splits. So the smallest field over which a polynomial splits is called the splitting field of that polynomial. So yeah, so what is the splitting field of the polynomial x square plus 1 over Q, that is? Any answers? What is the splitting field of x square plus 1 over Q? So what is the smallest field where this polynomial splits as a product of linear factors?
Q root minus 1.
Exactly. Q of I is where this polynomial splits completely, and that is the smallest field possible. So now this depends on the base field, right? So it's Q square root of minus 1 is the smallest field where it splits over Q. So suppose my base field is R now. So in that case, which is the smallest field where this splits? So the splitting field has to be an extension of the base field. So now the question that I'm asking is, what is the splitting field of x square plus 1 over R? So now the extension that I'm asking for is an extension of R. So which is the smallest field over R where this polynomial splits completely? It cannot be Q square root of minus 1 because Q square root of minus 1 is not an extension of R. So which would be the smallest field?
Odd only.
It doesn't split in R, no, because the roots of the polynomial are plus I and minus I. So they don't live inside R. So it has to be an extension of R which contains the roots. So in this case, it would be the complex numbers. That is the smallest extension of R which contains the splitting field, which is where the polynomial x square plus 1 splits. Okay. So there's this theorem which says that any two splitting fields of a polynomial over F are isomorphic. So this is just a technical thing. I am not going into the proofs of any of this. Okay. So, all right. So now we look at the Galva groups of certain polynomials, or at least try to understand what Galva group of a polynomial looks like. Okay, so what is this notation gal f? Okay, so Galva group of a polynomial is nothing but the Galva group of the splitting field of that polynomial over F. So here F, as I said, is always Q. So yeah, Galva group of a polynomial is the Galva group of the splitting field of a polynomial over F. So here we can look at this polynomial x square minus 2. The splitting field of this polynomial is Q adjoint square root of 2. The roots of this polynomial are square root of 2 and minus square root of 2. So by what I had told before, any element of this Galva group simply permutes the roots of this polynomial. Like it cannot take square root of 2 to anything else but minus square root of 2 or to square root of 2 itself. So the only two automorphisms possible of q root 2 that fixes the set of rational numbers are these two. You have the identity where 1 goes to 1 and square root of 2 goes to itself, and the other one where it permutes, it interchanges square root of 2 and minus square root of 2. So then the Galva group of q root 2 over q has exactly two elements. So there was a slide before this one, which I missed, where I have to discuss what that automorphism is. Okay. Yeah. So by whatever we had discussed before, if f of x is a polynomial and if L is the splitting field of that polynomial, and if x, which is alpha 1, alpha 2, alpha n, they're all n distinct roots of f of x in L, then what the elements of Galva group does is just to permute the elements of x. So that is for every element sigma of x equals x itself. That is, as a set, it is permuted. So is that clear? This doesn't mean that sigma sends alpha 1 to alpha 1 or alpha 2 to alpha 2 or anything like that. But as a set, it fixes the elements of Galva group would fix that set. Is it okay? Like, does anyone have a problem with that statement? Sigma of x equals x?
Any example?
Yeah, so example we'll see in the next slide. So what I'm saying is, this just follows from that earlier remark that I made, which says that elements of Galva group just permutes the roots of a polynomial. So roots of that polynomial can only go to a different root of the same polynomial. So x is the set of all roots that exist, that live inside L. So what the Galva group can do is only permute them, like send them to each other. So that is what I meant when I said that sigma of x is x. So it doesn't mean that it is identity. Okay. So now we have a map from the Galva group to the permutation group of that set. So that set has n elements. So you can look at alpha 1 as 1 and alpha 2 as 2 and alpha n as n. So that is just a set with n elements. So the permutation group of that set would be Sn. So what we are trying to do is we are trying to give a map from the Galva group of L over F into the set of permutations of the roots. So the map is, you have an element of the Galva group and that goes to sigma restricted to x. Now what does that notation mean? So suppose you have two roots. Suppose you have alpha 1 and alpha 2. And what your Galva group does is just permute those roots. So suppose your sigma is an element such that it sends alpha 1 to alpha 2. So then this map, sigma going to sigma restricted to x, that would be your sigma is going to 1, 2, the element in your permutation group, 1, 2. That is 1 going to 2. Is this okay? I mean, this homomorphism is important. So did you understand the homomorphism? You can think of that set with n roots to be, your numbers 1 to n. And if your sigma takes the first root to the second root, then this map would be sigma going to the element 1 going to 2 in your permutation group. Is it okay?
Ma'am, repeat please.
Okay. So, okay. So this map that I'm trying to define here, that is from the Galva group of this the splitting field over F to the set of permutations of the roots. So I'm saying that the polynomial has n roots and all the roots live inside L. So you just have to see what an element sigma from the Galva group does to that set. So I think there's an example after this. So I'll just go to that. So yeah. So yes. So yeah, so we can look at this example, x square minus 2. The splitting field of this polynomial is q root 2. So the roots are square root of 2 and minus square root of 2. And any element of the Galva group would simply permute these roots. So the only two elements possible are these two, where the identity element is which fixes everything, and the other one is that sends square root of 2 to minus square root of 2. So now the homomorphism that we discussed previously would be you have two elements and you have to send it to two elements of S2, since here your polynomial has only two roots. So there Sx that we had over there, here in this case would be S2. So S2 has two elements, right? It is just the identity element and the transposition 1 going to 2. So here the map would be identity, which is not doing anything to anything. So it is just going to the identity of Sn, that is S2 in this case. And the other one is permuting those two roots. You have two roots. You can call square root of 2 as 1 and square root of minus 2 as 2. So what it does is it just permutes it. It sends 1 to 2, the first root to the second root. So that is why the map is sigma going to 1, 2. Is this okay? We have another example. We can see that too. But is the homomorphism, at least the idea of the homomorphism, clear as to what the map is between the Galva group of L over F to Sn? You're sending it to a permutation. You're just looking at what root goes to what, and then you're just writing that down as a permutation. So okay, we can look at another example. So we look at the polynomial x square minus 2 into x square minus 3. So the splitting field of this polynomial is q root 2 root 3, and the set of roots are square root of 2 minus square root of 2 square root of 3 and minus square root of 3. So now where can all these elements go? So we know that Galva group permutes the roots of polynomial. But is it possible that any root can go to any root? So here in this case, I'm saying that square root of 2 and square root of 3 are both roots of this polynomial, but no element of the Galva group can send square root of 2 to square root of 3. Any ideas why? So it's because the elements of Galva group have to fix the base field, that is the field of rational numbers. So you can look at if suppose there is an automorphism which sends square root of 2 to square root of 3, then what would happen? Sigma, you look at the image of 2. So sigma of 2 can be written as sigma of square root of 2 into sigma of square root of 2, which would be, if we allow this map, it would be 3. So the image of 2 is going to be 3, which is not allowed because we need our automorphisms to fix the set of rational numbers. So this permutation of roots is not allowed. So here, which are the ones that are allowed? So here, since square root of 2 cannot go to square root of 3, these are the only 4 possible permutations that you can have. The first one is that fixes everything. The second one just permutes square root of 2 and square root of minus 2 and fixes root 3 and the other 2. So corresponding to these things, you have these maps into elements of S4 because you have 4 roots over here. So the first one would be it doesn't do anything to anything. So it is just, sigma, it just goes to the identity of Sn, S4 in this case. In the second one, you're permuting the first and the second roots and fixing the third and the fourth. So it is a transposition 1, 2. The third one is you are fixing root 2, but permuting root 3 and minus root 3. So the corresponding element in S4 would be 3 and 4. 3 going to 4, the transposition. And the fourth one is you're permuting both. You're sending square root 2 to minus square root 2 and square root 3 to minus square root 3. So the corresponding element in S4 would be 1, 2 into 3, 4, the product of transpositions. So here the Galva group is isomorphic to Z2 cross Z2. Is this okay? Or at least, vaguely, do you think this is true? Okay. All right. So there was an assignment, a home or thinking exercise sort of thing, where you have to figure out what the Galva group of x cubed minus 2 is. So I have given the answer. It is the permutation group on 3 symbols, and it's the entire group, like it is S3. So this polynomial, as you know, has 3 roots, and I'm saying that the Galva group of this polynomial is S3. It allows all possible permutations of roots. So you can figure that out.
Sigma 1 to sigma 6 can get.
Sorry? Sorry?
No, ma'am. Okay.
Okay. Okay. So now I had mentioned before at some point, I suppose, about what a solvable group is. So solvable group is nothing but a group G is said to be solvable if there exists such a sequence of subgroups which start with identity and end with the group G, such that each of those each of those subgroups in between are normal in the next one, and that quotient Gi by Gi plus 1 is abelian. So this is some technical condition. So such a group is called a solvable group. If you have a bunch of if you have a series, actually, a sequence of normal subgroups that are contained in each other, and the corresponding quotients are abelian. So such groups are called solvable groups. So the most obvious example of a solvable group would be any abelian group, because the quotient is always going to be abelian, and since it's abelian, all subgroups are normal. So any abelian group is solvable. And I don't know if you know this fact that an for n greater than or equal to 5 is simple. That is, it has no non-trivial proper normal subgroups. So are you aware of this fact? Or you can just black box it for now, that an has no non-trivial proper normal subgroups. So since you do not have a sequence of normal subgroups, and an is not abelian for n greater than or equal to 5, this group cannot be solvable. So there is a note which says that subgroups of solvable groups are solvable. So since ans are not solvable, Sns can't be solvable either. Because if Sn was solvable, then as a subgroup, an should also be solvable. But since ans are not solvable, Sns are also not solvable. So these are two important theorems which I'm just going to state. So the theorem is that if you have a polynomial fx in fx and it is solvable by radicals, then the Galva group is a solvable group. So did I tell you what solvable by radicals mean? Or did I skip over that slide? Do you know what solvable, when is a polynomial said to be solvable by radicals? So polynomial is said to be solvable by radicals if the splitting field of that polynomial is a radical extension over f. So if you get the splitting field by sequentially adding nth roots of um, elements, then you call such a field, um, then you call such a polynomial solvable by radicals. That is, yeah. So if all the roots of that polynomial are in some radical extension, then you say that that polynomial is solvable by radicals. So the theorem says that the Galva group of F is a solvable group. So this is an exercise in group theory and a little bit of field theory. We won't get into that. So this is just a theorem that says that the Galva group of a polynomial is a solvable group. So it satisfies those two conditions that I had mentioned before. You have a sequence like this and you have this quotient to be abelian. Okay. And there is this other result which talks about the number of elements in the Galva group. So if f of x is a polynomial and L is the splitting field, then the cardinality of that Galva group is equal to the dimension of L over F as a vector space. So these are two results that I'm going to be using in what I'm about to say next. So this is a theorem of Abel. So what Abel said was there exists a quintic polynomial over Q that is not solvable by radicals. So that means that he gave an example of a polynomial which that is not solvable by radicals. That is, the splitting field of this polynomial is not a radical extension of Q. So the polynomial that he supplied us with was x to the 5 minus 6x plus 3. So this is a polynomial with rational coefficients, and this is an irreducible polynomial over Q. So there is some criteria called the Eisenstein's criteria, which says that this polynomial is irreducible over Q. That is, it has no rational roots. So what we can note is we can look at various values of this polynomial. So if you draw the graph of this polynomial, you can see that f of minus 2 is a negative number and f of minus 1 is a positive number. So by intermediate value theorem, you get one root that is between minus 2 and minus 1. Similarly, if you look at f of 1, then that is a negative number. So again, you have a root between minus 1 and 1. And similarly, f of 2 is a positive number. So again, you have a root between 1 and 2. So you get at least 3 real roots. And you can see that the graph of this function does not intersect the x-axis anymore, because as you go towards the negative side, it just goes down to minus infinity. And as you go up the positive side, it shoots up to plus infinity. So this does not intersect the real line anymore. So then we can say that this polynomial has exactly 3 real roots. So since this is a degree 5 polynomial and it should have 5 roots, the other 2 are complex roots. Okay. So yeah, so we look at the splitting field of that polynomial. We don't know what it is, but yeah, so there exists a splitting field, and we look at that, and let alpha be a root of that polynomial. Then then Q alpha, the dimension of alpha, the dimension of Q alpha over Q is 5. So this is because alpha is a root of a 5th degree polynomial. So this is Q alpha is a vector space over Q, and since alpha satisfies a polynomial of degree 5, it cannot have a dimension that is greater than 5. And since alpha, this polynomial is irreducible, So this is a result which says that if you have an irreducible polynomial of a certain degree and it satisfies, and if alpha satisfies that polynomial, then this degree equals the degree of the polynomial. So one way is to see that it cannot be greater than 5 is that alpha satisfies a polynomial of degree 5. So alpha to the 5 minus 6 alpha plus 3 is 0. So you cannot have the degree of extension greater than 5. That is also a result that says that the degree of extension is at least 5. So this extension has degree equal to 5, Q alpha over Q. So now we apply the Tower law. L over F is the dimension of L over F equals the product of these two. So then this number, the dimension of L over F is divisible by 5. And we saw in that theorem that the cardinality of the Galva group is equal to this dimension. So I don't know if you know these results, like there is this result by Cauchy which says that if you have a group, a finite group, and if you have a prime which divides the order of the group, then there is an element of that group. There is an element of that order. So by that result, you have that the Galva group of F contains an element of order 5. Now we also have that homomorphism that we discussed before, where you were sending elements of the Galva group to Sn. Here in this case, it is 5 roots, so S5. So this Cauchy's theorem says that the Galva group of F, it contains a 5 cycle. A 5 cycle is an order 5 permutation in S5. Okay, so that is one thing. And you can also have the element of Galva group that fixes all the real roots and just exchanges the complex roots. So then that would give rise to an element, a transposition. You're fixing all the real roots. It has 5 roots. You fix all the real ones and you just exchange the complex roots. So inside S5, as an image of this homomorphism from Galva group to S5, you get a 5 cycle and a 2 cycle. So it's known that S5 is generated by any 5 cycle and a transposition. So these are all results in group theory, which I don't know if you have seen, but they are, interesting results. So once you know them, this proof becomes very obvious. So now, in case you don't know it, you can just, believe me. So S5 is generated by any 5 cycle and a transposition. So you get a 5 cycle and a transposition. So the image of the Galva group under that homomorphism has to be the whole group. So the conclusion is the Galva group is isomorphic to S5, which is not solvable as we had seen before because A5 is not solvable. So yeah, so by that theorem which says that Galva group of a polynomial has to be solvable, we can say that the polynomial that we described before, that is x to the 5 minus 3x plus 6, that polynomial is not solvable because the Galva group of that polynomial is S5, which is not a solvable group. So that was Abel's proof of the existence of a quintic that cannot be solved by radicals. So thank you. And you can ask me questions or whatever it is.
Ma'am, in Cauchy theorem, 5 roots can also for n roots?
So it should be a prime number. So this is true for any prime. So if you have a group, a finite group, and if you have a prime number which divides the order of that group, then there is an element of that order. That is the statement of Cauchy's theorem, Cauchy's result or whatever. So it's not true for any n, that n has to be prime. I mean, oh, so n is the order of the group or the prime? So for any prime dividing the order of the group, that result is true, that there is an element of that order, of the prime order, that is.
Thank you, Ramya ma'am. Participants, if there are any questions, you can ask to the resource person or you can ask your doubt in the chat box.
I mean, should I stop sharing?
Oh, yes.
Yes.
Okay.
Is suggesting a book for field theory?
So for an elementary introduction, I think Dammit and Foot would be very good because it has almost all basic algebra that you would want to learn. If you want to learn Galva theory, then you can maybe look at Galva theory by Emil Larten. I mean, Dammit and Foot is a good enough book, and if you want like other algebra books, you may look at Lang or yeah, I mean, Dammit and Foot is very good for an initial introduction into the subject, if that is what you were looking for.
Any more questions from participants?
I think there are no more questions.
Okay, so I think we can wind up the session. So thank you, Ramya ma'am. That was really a wonderful talk. You explained the Galva theory in a very simple way, and I'm sure that will be beneficial to all of the participants present here. So on behalf of entire participants present here and all the faculties of Sacred Heart College Chalakudi, I express our sincere gratitude towards you. So thank you for delivering such a nice lecture.
Thank you. Thank you so much for inviting me and listening for all this while.
Thank you, Ramya ma'am.
Thank you. Thank you.
So dear participants, please find the feedback form in the chat box. And the next session will be on Monday. So see you on Monday. So thank you to all.
Thank you.